Where we'll introduce you to an often overlooked flow technology, Turbine. It may not be what you think it is, so in the next 35 to 45 minutes, we hope you'll learn how to take another look at turbine flow measurement and how it can improve your process and product quality. Our presenter today is Sandy Kelly. Sandy's the North American Sales Manager for Hoffer. Hoffer specializes in high-performance flow meters for liquids, gases, cryogenic flow applications. Sandy has 20 years of experience in flow measurement with an emphasis on turbine flow technologies. She's published multiple papers for the International School of Hydrocarbon Measurement discussing the use of turbine flow meters for custody transfer. We will be muting the phone lines. If you have any questions and would like to unmute yourself, all you have to do is hit *6 and you will be unmuted. At the end, we will unmute everyone. So if you want to save up your question, feel free to ask it at the end. With that introduction, I'm going to turn the screen over to Sandy and let her start the presentation. Sandy, you should now have control of the presentation.
I think I do. Can you see my screen, everyone?
It'll probably take a second to transfer over.
Very good.
Why isn't it not transferred over yet?
I don't know. Let me see.
There we go. I got it now.
Okay.
Everybody should be able to see it now.
Okay. Okay. Good morning, everyone. My name is Sandy Kelly. I work for Hoffer Flow Controls, and I would like to begin my presentation by thanking you for attending my presentation. I realize everyone is busy, and I put together the presentation with that in mind. What I'd like to try to hit on are the features and the benefits that I think will be important to the audience of people that are attending this morning. So thank you for joining me in my presentation. Uh-oh. Okay. This morning I would like to cover the history of turbine technology and review the technology, the principle of operation. I'd like to discuss the benefits specifically of the Hoffer turbine product line. I'd like to compare various types of flow meters, turbine flow meters, with each other. And then I'd like to discuss why the Hoffer product line is unique. And I will begin the presentation by quoting Mark Twain and kind of a tongue-in-cheek format. The rumors of our death are greatly exaggerated. And I say that regarding turbine flow meters because the portrayal of turbine technology in today's environment is that the technology is an older technology, and we will discuss that. It was developed in the 1940s. But I think what's more important is that the editors of online websites and of print material like to talk about new. They like to talk about new technology, and we as users like to hear about new. But in the effort to share with users new is better, some established technologies take a hit. And I think turbine meters as a flow category may fall within that situation. So turbine meters continue to be a viable flow solution for many users today, and we'll discuss some of those applications this morning. And I'd like to specifically cover why you should consider using turbine flow meters for any clean liquid, gas, or cryogenic application. The original turbine flow meter was developed in the 40s for the U.S. Navy. And as flight patterns became longer and longer, obviously it became more critical to know how much fuel was on board. So a gentleman by the name of David Potter developed and patented the first turbine flow meter for the U.S. Navy. And Potter Aeronautical, the company that started developing the first turbine, licensed a number of companies in the 1970s. They licensed Kent in the UK, they licensed Smith Meter, and they licensed several other companies to manufacture turbine flow meters. And Potter Aeronautical went out of business in the late 1960s, and Hoffer Flow Controls was started in 1969 by the former production manager of Potter Aeronautical. So the company of Hoffer has been around for a number of years, and some of the applications that we've developed over the years continue to be flight qualified liquid turbine flow meters for, as you see here, the stealth bomber. Hoffer Flow Controls is a privately held company. We are located in North Carolina along the Eastern Shore, and we have a reputation in the industry for providing very high quality, high performance turbine flow meters. Some of the major markets our company serves include those listed on this slide: the oil and gas upstream and downstream markets. Cryogenic is a big SIC code for our company. Liquid cryogenics, primarily our meters can be found on bulk delivery trucks of liquid oxygen, argon, and nitrogen, and CO2, liquid CO2. Our meter is essentially the cash register on those cryogenic bulk delivery trucks. Other markets include pharmaceutical and biotech. We do quite a lot in military, water and wastewater, aerospace, automotive manufacturing. Our meters, interestingly enough, are mounted on a number of NASCAR automobiles and also on drag cars for monitoring the fuel usage and the fuel consumption on those race cars. And for the power industry, our meters are typically used to control the NOx emissions, or on the fuel measurement side in power generation. Our company has a history for being able to design and build custom flow meters in a relatively short period of time. Some examples of our custom design meters include high-pressure units. We've designed and supplied high-pressure turbine meters that are rated up to 60,000 PSIG. And we've worked with all types of exotic alloys and ultra-high velocity flow meters that we've supplied primarily to NASA for rocket propulsion. They typically are working in very high velocities, and we've designed flow meters up to Mach 0.5, which is half the speed of sound. So we do some very unique things in terms of modifying the flow meter internals to support those very high velocity flow applications. A basic review of the technology itself: a turbine meter is measuring velocity of the moving fluid, and they're typically used in clean, low to mid viscosity applications. We typically cap our meters at about 100 centistokes. Any applications that are more viscous than that tend to become extremely nonlinear and non-repeatable. Liquid meters are typically designed for velocities up to 20 feet per second, and our gas meters are typically designed for velocities up to 250 feet per second. Here's a cutaway shot showing the basic principle of operation, and what we have here is an inlet side of the flow meter, and then we have a flow straightener. In our case, our typical flow straightener is a tube bundle. We have a through shaft that supports the flow meter internals. You'll see a lock nut at the end of that through shaft on the inlet and then on the outlet side of the meter. We have a rotor assembly mounted directly under a pickup coil. So as the fluid or gas moves through the turbine flow meter, the rotor assembly rotates and the pickup coil produces pulses. You can relate the frequency of the pulses to flow rate, and you can relate the number of pulses to flow total. With turbine meters, you're typically talking about some basic definitions in performance. Linearity is a measure of the accuracy of the device relative to the K-factor. So it's the percentage of deviation from the average K-factor. The K-factor is the number of pulses that the turbine flow meter produces per engineering unit. So, for example, an 1.5-inch turbine flow meter typically produces 230 pulses per gallon. On the repeatability, that's really important relative to turbine technology. That's a statement of the ability of the measuring device to display the same value of a measured variable under identical conditions. And for turbine meters, that's really where they shine. Turbine meters, precision machined turbine meters, are typically extremely repeatable. And we'll get into that discussion a little bit further along. So we mentioned the K-factor is the number of pulses per engineering unit, or pulses per gallon. This slide represents a plot of the K-factor relative to flow rate. So you can see that at the low end of the flow scale is where the K-factor for a turbine meter starts to deviate and become nonlinear. And it's relatively linear as it approaches a maximum rated flow capacity for that size turbine flow meter. And once you exceed the rated capacity or flow rate of that turbine flow meter, it becomes nonlinear again. So typically this would represent a K-factor over a 15-to-1 to a 20-to-1 turn-down ratio between maximum flow and minimum flow. And some other variables and performance characteristics that we're looking at relative to flow rate are your pressure drop through the flow meter increases as your flow rate increases. Your frequency output coming off of the pickup coil increases relative to flow rate, and the amplitude of your signal increases with flow rate as well. Why use turbine meters when there are so many other choices, and how does a user go about selecting the best flow meter for his or her particular application? Well, one of the things that Hoffer really specializes in, and our forte, is in the supply of application-specific flow meters for a particular application. We do not typically approach a flow application with a standard product line and try to make the standard product fit within the scope of that application. We take the specifics of the application, and then we try to design and supply a flow meter pertinent and appropriate for that particular application. So we have a line of mini flow meters for very low flows. Our standard HO series covers flow rates from 0.35 all the way up to 12,000 gallons per minute. We offer custody transfer gas turbine meters, and we have a line of 3A certified sanitary meters. This slide is included in my presentation primarily to show you the wide selection of product categories that are available within turbine technology by simply varying the housing on the flow meter and by varying the flow meter internal design. You have a lot of flexibility in terms of what you can do with the turbine flow meter. Let's talk specifically about some of the advantages of turbine meters over some of the other technologies that are available to users today. And one area where turbine meters are considered to be perhaps a better choice than other technologies is in terms of performance. They're extremely accurate, and they're commonly used because of this accuracy and this linearity. They're typically used for custody transfer on pipelines and custody transfer as other goods and liquids pass from one supplier to a customer. So oftentimes turbine flow meter systems are used basically as the cash register in lots of custody transfer applications. So performance is an advantage. Another area where turbine meters really shine is they respond very quickly to changes in flow conditions. So the response time is very important on turbine meters. And the reason they respond so dynamically is in the case of the Hoffer turbine, we precision machine all of our rotors. They're all machined, they're not cast. So they're relatively light, and they, because of that fact, they respond very dynamically to changes in flow rates. So they respond dynamically to changes in flow rates. Those changes can be measured in milliseconds, and turbine meters are commonly used by NASA for rocket propulsion. Another advantage of turbine meters as a class of measurement devices, they can be designed to tolerate and work reliably in applications where there's a lot of shock, vibration, and temperature extremes. And an example of that would be in cryogenics again. As I mentioned earlier, our company supplies turbine flow meters and totalizers to the cryogenic market for use on their bulk delivery trucks. When we pioneered the use of turbine meters back in the 1970s, prior to that time, most of the cryogenic companies were billing customers as a function of the weigh scale. They'd load product onto the truck, make a delivery, go to a scale, and figure out the difference in weight and bill based on that function. Today, the majority, well, actually all cryogenic trucks in North America and most throughout the world are outfitted with flow measurement systems, and in many, many cases, those are Hoffer flow measurement systems. They are designed to tolerate the over-the-road shock and vibration conditions that will obviously be seen by the truck as it makes its delivery in all kinds of weather conditions, from very warm temperatures to very cold temperatures. The cryogenic liquids themselves are very, very cold liquids, so our meters had to be designed and are designed to tolerate working temperatures as low as minus 450 degrees Fahrenheit. And as I mentioned earlier, our systems are basically the cash register on many of the bulk delivery trucks. One of the keys to our success on this particular application was finding a bearing within the meter that would work in that very cold environment. And not only are cryogenic liquids by definition extremely cold, they're also very dry fluids. So we had to find a bearing that really did not rely on the lubricity of the fluid to lubricate the bearing itself. So what we did is we found a ceramic hybrid ball bearing that has a molybdenum lubricating agent impregnated into the bearing. So the bearing is not relying on the fluid for lubricity. It's actually a self-lubricating bearing. And we use that bearing in our cryogenic meters, and we also use that shielded ceramic self-lubricating ball bearing in our gas meters. Another advantage of turbine meters is reliability. They can be designed and fabricated with high degrees of reliability. In fact, on this particular slide, this shows a subsea blowout preventer. Hoffer, about a year ago, after Horizon, was contacted by a major manufacturer of BOPs, and that particular manufacturer of blowout preventers was experiencing leakage with mag meters that they were using on their BOPs. The BOP includes a closed loop flow path, and that closed loop actually controls the opening and closing of valves. And they monitor that closed loop with the Flowmeter. They had been using mag meters, but as I mentioned, those were leaking. So well, what happened was we were contacted and asked to design a meter specifically for this subsea application. And this is an interesting application because it's high pressure externally and it's high pressure internally. These BOPs see about 9,000 PSI externally, and the control loop with control fluid, that closed loop that I mentioned, they're operating that at about 6,000 PSI. So you'll notice that the schedule of this Flowmeter housing is very thick. These are SAE fittings that are rated to higher working pressures. And then there's a subsea connector that's designed into the riser. But reliability would be an advantage of a turbine meter, perhaps over another type of meter technology. The meters are designed and can be designed and supplied to be extremely robust. Hoffer has supplied Navy flow meters, or I should say turbine flow meters, to the U.S. Navy for every class of the U.S. Navy vessel that is in our fleet. We have flow meters that are used to supply the fuel to the engines, and we have flow systems that are on ships for missile cooling applications. We've supplied flow meters for the reverse osmosis water purification plants on ships. So they can be built, obviously, for applications that are, again, in a harsh environment and that are subject to shock and vibration. And what we did to make the flow meters more robust and capable of meeting military standards for high shock and high vibration is we altered the design on the internals of the flow meter. You may recall that cutaway shot earlier where I showed two bundles and a through shaft and the rotor assembly. Well, the Navy design meter is similar, but it is different in that it is a design that is more robust, and it is also a design that has been tested to meet military standards for shock and vibration. So you'll notice that the flow straighteners are now, instead of two bundles, they're vaned assemblies. There's a conical deflector cone on the upstream side of the flow straightening assembly, a rotor assembly that has heavier blades on the rotor itself. The blades are thicker than on our standard industrial meters. And this flow meter has to be suitable to tolerate conditions that if anything were to pass through the meter, the internals would not be pushed out of the ID of the housing. So there's a shoulder on the downstream side of the meter ID of the housing, and this flow straightener then gets inserted into the flow meter housing, and the actual flow straighteners rest on a shoulder in the ID of the housing. Then the rest of the internals are placed inside of the flow meter, and then there's a threaded insert that threads into the ID of the flow meter, so that this is considered a fail-safe design that we had to come up with for shipboard applications. Another advantage of turbine meters is wide rangeability between your minimum and your maximum flow rates. We are capable of obtaining flow turndown ratios of up to 100 to 1 for our flow meters, and that's very impressive because that's a repeatable flow range. And I'll show you an example of that. This is our size selector chart for our 1/4-inch meter through 12-inch meter. This is one product line that our company offers. This happens to be our HO series of liquid turbine meters. And I've highlighted the 1-inch size. And what you see here is a 1-inch size flow meter with a magnetic pickup coil. That's the sensor that mounts over the rotor assembly. And we offer a different type of pickup coil as an option. A modulated carrier pickup coil is offered, and the benefit of this particular coil is it eliminates the magnetic drag characteristic that you see at the low end of the flow curve. Remember when we looked at that slide earlier and we saw how the linearity dropped off at the lower flow rates, the reason the K factor and the linearity drops at the low end of the flow scale, there are a couple of reasons, but one of the reasons is the drag characteristic from the mag pickup. So if you eliminate that drag characteristic by going with a modulated carrier pickup coil, you'll see something very interesting. You'll see on this 1-inch example, the linear range with the mag coil is the same. It's 4 to 60 gallons per minute. The repeatable flow range on the 1-inch meter with the mag coil is 2 to 75 gallons per minute. Here is the repeatable flow range of a 1-inch meter with a modulated carrier pickup coil. So we've eliminated the drag characteristic. That's a repeatable flow range of 0.75 to 75 gallons per minute. That's the 100 to 1 turndown ratios that I'm referring to, and that's what makes the turbine flow meter, when configured with certain options, so powerful for certain applications. Because keep in mind, that's a repeatable flow range. So what does that mean? Well, that means that that 1-inch flow meter, if you were to calibrate it over the range of 0.75 to 75 gallons per minute, and take multiple calibration points and repeat those points, this curve would look identical, would plot the exact same curve to within plus or minus 0.1%. That's the repeatability on our HO liquid meters. So what that means to a user is, okay, I've got this 100 to 1 turndown range. It's a repeatable curve to within plus or minus 0.1%. Now I can linearize my flow meter with a smart piece of electronics. So I can correct for this known nonlinearity at the low end of the flow scale because it's repeatable. So that is, that's actually pretty powerful. There aren't many meters that can offer plus or minus 0.1% of reading over turn down ratios that extreme. Another advantage of turbine meters, they're typically spec'd out in terms of linearity as a percentage of reading versus other types of flow measurement devices that are spec'd out as a percentage of full scale. So as an example, you know, a meter at a flow rate of 100 gallons per minute, that's plus or minus 0.5%, that translates to 0.5 gallons. Well, 0.5 gallons at you know, 100 GPM is an accurate meter, but 0.5 gallons if you're operating over a 10-to-1 ratio, and if you're down around 10 gallons per minute, 1/2 of a gallon represents 5% of your measurement uncertainty. So there's a big difference in devices when you start talking about specmanship and full scale versus of reading devices. On this slide, I wanted to show that all flow meters are not created equal. There are lots of different meters that are called turbine meters, and basically they consist of a rotor and a sensor of some type, and they're counting pulses. Common design elements for a high-performance turbine flow meter, such as the Hoffer product line, include precision machine components. The rotor assemblies are all precision machined. We don't use any cast components. That includes the rotor assemblies. And of course, cast rotors are heavier than precision machined rotors, and heavier rotors mean slower dynamic response to changes in flow rates. The design of the rotor assembly itself, let's talk about that. The Hoffer meter, as you saw on those cutaway shots and on the Navy meters, we utilize a flat blade design on the rotor assembly, as opposed to some other manufacturers that offer curved blades on the rotor assemblies. Curved blades are excellent for extracting energy, which is why you see them used on jet engines and things like that. But the trade-off relative to curved blades is they have a significantly higher pressure drop than a flat blade. So lower pressure drop with the design of our rotor assemblies. Our rotors can be customized for a particular application by making the blades heavier. And we commonly do this in our line of oil patch meters, where we're actually metering slurries at low pressures. So if we know that a customer, for example, may have suspended particulate in their process liquid, we can customize the rotor assembly. We can make the blades shorter to allow for clearance of the particulate, so we must know the maximum particle size, and we can make the blades thicker. On our rotor assemblies, because they are precision machined, we can basically customize them and make them available in multiple blade angles relative to the hub of the rotor. So for example, on our gas flow meters, we offer 4 different rotor assemblies. We offer a 15, a 20, a 25, and a 30-degree rotor. And each various blade angle rotor provides a different flow range. So within the scope of our gas meter product line, we can basically tweak that size to be most appropriate for that particular gas flow application. So the steeper the blade angle, the lower the flow rate capability of the meter. So if you have a customer with an application where his line size is larger relative to his lower flow rate, you can go with a steeper blade angle to basically obtain the lower end of the flow scale for that particular application. And we also offer bladed and rim-type rotor assemblies. And here is a slide showing the difference between a bladed rotor assembly and a rimmed rotor assembly. Basically, the rim incorporates a shroud around the OD of the rotor. And what we do is within that, that piece around the rotor assembly is we put buttons, magnetic material around the rim, and basically we can control the number of pulses that the meter produces by controlling the number of buttons that we put into the rim. That type of design is commonly used for custody transfer. So in conclusion, some of the reasons that we've discussed this morning that would be appropriate perhaps for selecting turbine meters over some of the other types of technologies that are available would be if accuracy is important, if you need a robust flow meter, you require very dynamic responses because you have an application where you change flow rates regularly, you require a wide turn-down flow range, you have a specific footprint or space in which the flow meter must fit. We commonly supply longer flow meter housings. The blowout preventer application was a case in point where we had to fit a specific footprint to for that particular application. And if you want a flow meter that is light in weight and easy to install, turbine meters should be considered as a possible solution for you. And that's all I have for you this morning. Thank you for your time.
Sandy, thank you very much for your presentation. At this point, I'll
unmuted
all of the callers and see if we have any questions. So if anybody has any questions, I have unmuted the line. Feel free to ask Sandy.
This is Pat Gorman. I have a question. One of the slides showed the design of having thicker blades for flow fluids that would contain some particulate matter.
Right.
I was under the understanding that turbine flow meters are best applied for clear or clean liquids.
They are. The applications that Hoffer gets involved with, where I mentioned there are slurry applications or are primarily oil patch applications, where they've fractured the well, and after they've fractured the well, they pump at very low pressures slurries to into the well to keep the fractures suspended and to support the fractures from collapsing. So they use a variety of different slurries for that application. Some are cement slurries, some are sand slurries, some are proprietary slurries. But what we do for those oil patch applications is we make we shorten the blades on the rotor and we make the blades heavier. And those customers actually will run a low-pressure Victaulic fitting flow meter until they lose the signal. So basically what's happened is the blades on the rotor has worn to a point where the coil no longer can see the blades. And they don't really have a lot of options for that application because it's such a harsh environment. So turbine flow meters are commonly used in that application. I've seen turbine meters used on a couple of industrial applications where we knew that the customer had some fine particulate. And in those applications, what we've done is we've gone with a sleeve bearing, a tungsten carbide sleeve bearing, and we have made the blades shorter because the customer has shared with us his maximum particulate size. So if there is some fine suspended particulate in an industrial application, we would look at that and we could potentially offer a meter for that application.
Thank you.
Does that answer your question?
Yes, it does.
Okay.
Yeah, this is Ravikant at Marichem. Up to how much percent slurry can you go in terms of suspended solids for a turbine meter application? Even, the particle size will be small.
Well, I can't answer that because I don't know. I honestly can't answer that question. I don't know the percentage of slurry that our meters can handle. I really don't. I do know that as the flow meters become larger, the particulate clearance between the ID of the housing and the blades on the rotor, that clearance becomes larger. So obviously larger meters are capable of tolerating more particulate than some of the smaller meters. But in terms of your question, I'm sorry, I'll have to get back to you on that. And I'd be happy to do that.
So the recommended practice is only for clean fluids?
Yes.
And what is the maximum size that you can go to?
Maximum size flow meter?
In terms of pipe size, yeah.
Well, we've designed and supplied up to 14-inch inline flow meters. The chart that I showed showed our standard meters up to 12-inch size, but we've actually supplied 14-inch flow meters that I'm aware of. And we supply a line of insertion flow meters for line sizes from 4-inch up to 72-inch. But that's an insertion type turbine.
Right. Thank you.
Welcome.
Hi, this is Sanchita from American.
Yeah.
I had a question about the use of turbine flow meters for the gas application.
Yes.
What about the pressure and temperature compensation? Is it needed for these meters?
Yeah, well, it depends. There are two different ways of approaching a gas flow application. We have some users who simply purchase our meters with a totalizer rate indicator, and they read out in volume, or they read out in actual cubic feet. But we have many users who are doing custody transfer of natural gas, for example, in the power industry, and all of those systems are supplied with turbine flow meters that have been calibrated at the user's operating density. So the K factor is supplied for the specific density that the users are operating at. And then we have a flow computer that is AGA 7 compliant. So it does the mass flow calculations with a temperature input, a pressure input, and the volumetric flow meter input. It then calculates mass flow according, to the AGA 7 requirement, and our computer also will correct for supercompressibility, or AGA 8. So we have many systems that are mass flow for gas, and we've supplied many that are volumetric. It really is, it depends on the application and what the user wants.
Yes, so it means that with the AGA8 system, we have to manually input the pressure and temperature, or how does it do it? How the compensation?
It performs mass flow calculation. So you're dealing with a volumetric input from the flow meter, and then you're inputting temperature and pressure, and you're calculating mass flow.
Okay, so that means we have to input the pressure and temperature at that point to get the mass flow, right?
On a turbine-based system, if you want mass flow, you have to temperature and pressure compensate with a flow computer, or you can do it on your own. But yes, you have to look at volumetric flow and then flowing temperature and flowing pressure.
Okay. And Is there any upstream and downstream requirement? For this meeting?
AGA 7, if it's custody transfer, AGA 7 defines 10 up and 5 down. And the American Petroleum Institute, you know, for liquid custody transfer has the same rule, 10 up and 5 down. 10 pipe diameters upstream, 5 pipe diameters downstream.
Okay. And regarding the slurry application,
yes.
Is there any, what is the material of the blades that you generally use?
The rotor assembly is made of a magnetic grade of stainless steel. All the other components are made of 316. And the typical rotors materials we work with are either 17.4 pH stainless or nickel 200. So we work with both of those for our oil patch meters.
Okay. Okay, thank you.
Thank you. Are there any other questions that I can answer?
Yes, this is Alex Hoffer from Thomas Engineering. I do have a question on the pharmaceutical application.
Okay.
Are there flow meters available that are truly designed to BPE standards rather than 3A?
To what?
BPE standards, ASME BPE, that's pharmaceutical standard rather than milk and dairy such as 3A?
Yeah. I don't know. I'm not sure.
It sounds like I know.
Yeah. I am going here to an application note on our website, pharmaceutical. I know we've supplied a lot of our 3A meters to the pharmaceutical for ultra-pure deionized or water for injection, and some of our users have used the flow meter with 316 with a very fine or highly polished finish.
Right.
And we have other users who really don't want any stainless in the line. So for those users, we offer a line of Teflon flow meters so that stainless doesn't come in contact with the purified water. What we do is we use a Teflon liner, and then we make all of the internals out of Teflon for some applications.
Okay.
Okay. Are there any other questions?
Yes, I have one other question, Sandy. This is Ravikant again at Americhem. We wanted to share this information with some people in our organization, and I was wondering if you can, give us some contact or, technical papers or brochure where we could get some follow-up information that we could share with our other engineers in our company.
Sure, I can help. I can help you with that.
Okay. We can do it offline if you want. You can give us a phone number or a contact or an email or something. Or.
Yeah, of course. I'd be happy to help.
Ravi, I've got your email, so we'll be back in touch after this webinar.
Okay, it's arkant@americhem.com.
Yep, I've already got it.
Right, and Sanchita is also with me in the same company. Okay, thanks.
Okay.
Yeah, please send us an email.
Okay. Are there any other questions that I may help with? Okay, I guess we're done.
If anybody does think of any questions afterwards, feel free to give me a call. Again, this is Mike DeLaCruz at Lessman. I can be reached at 800-9-LESSMAN or 800-953-7626. Later today, you will get some another email from us that links you to a recording of this session, so that if you want to go back and replay part of it to get some more background, you can. At this point, if there are no further questions, our presentation will conclude, and we thank you very much for attending.
Thank you very much for your time this morning. I really appreciate it. Okay, I'm going to log off. Bye.
Thank you, Sandy.
Okay, everyone. Have a good day.